Good afternoon, everyone, and thank you for attending today's webinar on subsurface investigation and geotechnical evaluation given by Adam Schneider from Atlantic Testing Laboratories.
So some of the topics we're going to discuss today are designing a subsurface investigation program, the different investigation methodologies that we have at our for use, review some boring logs and the information that's provided on them. We'll also talk about CPT equipment and CPT boring log review. Talk about some soil classification systems and engineering properties of the soils, and then discussion a little bit about what goes into the geotech evaluation report phase. When we talk about designing a subsurface investigation program, the biggest thing we need to come up with is the total number of borings that we're going to be doing for the project. When we start talking about different buildings, there's really no requirement in the building code. The number of borings is to be determined by the geotechnical engineer of record. As a rule of thumb, we generally look for one boring for every 2,500 to 5,000 square feet of building footprint. But again, that can be modified based on the type of building. Large warehouses that may approach 100,000 square feet or even greater than that. We can start stretching the number of borings out to one boring for every 10,000 or 200,000 or 20,000 square feet. And a lot of that depends on the consistency of the soil. So one thing that the geotech engineer typically does is goes through and reviews the soil conditions that they think are going to be in that area from soil maps or other sources that are publicly available, and even the history of the company that they work for. Our firm has a large database since we've been doing this since 1967 that goes back and includes hundreds of projects, and I guess thousands of projects really, that we have to go back and look at, and we can kind of determine what the conditions we expect might be in a certain area. Some of the other types of projects we do soil borings for is bridges. Generally, the number of borings we do for a bridge depends on the type of bridge, that it is. We like to see at least one boring per abutment. If there's a center pier present, we also try to do a boring for that, whether it be through the existing bridge deck or even from a barge mounted system in the water. The other thing that we have to consider with bridges is where the funding and where the review is going to come from, in the sense that, especially in New York State, the state DOT has very specific requirements about numbers of borings and depths, and they actually require 2 borings per abutment and on either side of the road. Retaining walls is another area that we do a lot of borings for, and it's tough to give you a guidance on the number of borings for retaining walls. A lot of it depends on the lengths of the wall, the heights of the wall, and a lot of different factors. So if you have those types of projects, it's very good to discuss it with the geotech engineer so that they have enough borings to feel comfortable with the design of what's going to be done. Roads, parking lots, and pavements are also another similar thing that we also struggle with a little bit, determining the total number of borings for, because the projects can vary from relatively small parking lots where maybe only 1 or 2 borings are needed to long stretches of road where you may be doing several borings per mile or even only a few borings per mile. When it comes to stormwater management areas, the general rule of thumb are provided in the DEC manual as to how many borings are needed. Those are readily available, and we can modify those, again, if the areas are very large. We've been doing a lot of solar fields lately. Generally for solar fields, we try to look for 1 boring for every acre or so of area, but that will also vary based on how many acres the project is and how variable the conditions are. So after we determine how many borings we're going to be doing, we then need to determine how deep we're going to drill. This is again going to be based on a lot of the conditions that we know, things that we know about the soils in an area, maybe the depth of bedrock that we anticipate. Maybe bedrock's not critical for that structure. Generally, as a rule of thumb, we like to go at least 2 times the width of the footing below the bottom of proposed footings. So if you're anticipating your footing to be 4 feet wide and 5 feet into the ground for frost protection, then your minimum depth of boring would be about 13 feet, and generally we round up to the nearest 5. So minimum of 15 feet for that scenario. Determining the seismic site classification is also important. The building code does not require 100-foot deep boring. You know, there's some misconception on that still out there, and that is what it requires the geotechnical engineer to know is the soil properties of the top 100 feet. And what I mean by that is if we hit bedrock at 20 feet, we know that we're not going to run back into soil below that. So we can use that knowledge to allow us to shorten up borings. We also know that if we hit very dense soils, we're able to lessen the depth of the borings as well. And that way, saving some cost and time when we're doing the investigation program. So the properties that we're looking for within that top 100 feet are either the soil shear wave velocity, the standard penetration resistance, or the soil undrained shear strength. And what we do then is determine the weighted average of one of those 3 properties to determine what the seismic site classification is. Seismic site classifications are broken down into 5 categories, A through F, but not to be confused with the seismic design classification, which are also A through F. Once we determine the site classification, then we have to determine the ground, the spectral ground response, which are returned based on the site address and the coordinates from the various websites that are available. New York State sites typically fall into site classes B, C, and D. Generally, we have glacial till and bedrock at shallow depths, generally less than 50 feet. That's not always the case. There are definitely some exceptions. The Onondaga Lake area in central New York and Syracuse area, we've drilled to find the bedrock there, and it's in excess of 300 feet. We have some very loose sands in the Albany area. Some of the river and stream valleys too tend to be areas where we have poorer soil conditions. And a lot of that's based on the geology of the state, in which we had a large glaciation, actually 2 of them, and they carved out a lot of the stream beds, and they have since, over the years, since the glaciers receded, filled in with looser sands and or silts and clays. So now we're going to get to question number 1.
All right, continue, Adam.
Okay. So question number 1 was true or false? Does a 100-foot soil boring need to be advanced to determine the seismic classification? And as I stated just a bit ago, that answer is false. We do not need a 100-foot deep boring. So after we determine how many borings we're going to be doing and what depths we're going to be advancing those borings to, then we didn't determine the methods that we're using to get those, whether we're going to do conventional soil borings, cone penetration testing, using a geoprobe for various different things, or test pits. So also, while we're on this slide here, if you notice that picture in the corner, that is what we refer to as an ATV mounted drill rig. It means it's an all-terrain vehicle. That is a unit that is mounted on tracks. It is, just for general reference, when people refer to these, the weight of that unit is somewhere around 15 ton. However, the ground pressure is less than what most people are when they're walking. So I've had personal experience where that rig, I was walking behind it. We were walking in about 4 feet of snow. It was only crunching in about 6 or so inches, and I was walking in snow up to my waist. So if that gives people an idea of what, when a drill refers to an ATV mounted drill rig, that's one of the options that we're referring to. So different borehole advancement methods that we have for conventional drilling, we can either use holostem augers or flush joint casing. There are some other methods that are out there, but those are the 2 most common. And when we talk about different sampling methods, which we'll get into a little bit more here, there's a couple of different sampling methods. For another point of reference, the drill rig in this picture here is a Geoprobe Model 7822 DT, which is a geotechnical drill rig that we have. We have 3 of these in the fleet. This is also what we consider an ATV mounted rig because it is mounted on tracks. The advantage to this one is it's smaller, lighter, and it's mounted on rubber tracks instead of the steel cleated tracks of the last unit. So therefore we can be a little bit more, it's a little bit easier to use when we have pavement and areas where there's grass or maybe some softer soils that we need to access. Holostem augers are one of the more common methods we use for advancing borings. Essentially what you have is you have a center sampling tube with auger flights that are formed around it. When we're advancing the augers, what we do is we advance them to the depth of where we're going to be taking the sample. You pull the center plug out, you lower the sampler into the augers, depending on the depth, depending on the type of sampler, advance that sampler, and then retrieve your sample, put the center plug back down, and advance the augers again. You can see in the picture how the set of them look on a pallet there. And when we refer to the size, we're referring to the interior diameter of the center sampling tube. So your most common sizes that you're going to see are 3 1/4 and 4 1/4 inch holostem augers, although we have them from 2 1/4 all the way up to 8 1/4 inch, depending on what we're trying to do with that boring. Some advantages of the holostem augers is they're pretty quick. Generally, we can advance 60 feet or so per day. So if you've got 20-foot borings, that's generally 3 to 4 borings a day. They're economical because of the speed. The other advantage, especially this time of year, is water's generally not necessary unless you get into certain conditions with flowing sands. It's a little bit difficult to drill with water when it's temperatures like we have up here in the North Country, which right now we're looking around 10 to 15 degrees and anticipated to go well below 0 over the next few. The other advantage you have is you can collect some rudimentary bulk samples if it's something that you need for the testing that you're doing. Generally, the maximum depth that you can advance holostem augers in a boring is around 100 feet. And part of that has to do with the way the joints are. If you can see in the picture, the way the joints between each 5-foot section is a keyed and bolted connection. And that connection has a little bit of flex to it, and therefore it allows it to move some. And therefore we try to limit it to 100-foot boring, so you only have about 20 of those joints put together. Now we'll come to question number 2.
You can continue, Adam.
Okay. So question number 2 was, how deep can you drill with holostem augers? And I hope everybody got that correct, which was D, 100 feet. So the other common method of advancing borings is using flush joint casing. There's 2 methods we can advance flush joint casing. One is driving it into the ground, either with, if you look at that picture, there's a 300-pound donut hammer there, or on those Geoprobe drill rigs that we actually have a hydraulic percussion hammer that can advance that casing. And what it does is, by either method, it's advancing the casing by driving it, by causing the soils to slightly liquefy in front of the casing so that the casing's allowed to advance. The other method that we use commonly is called spun-in casing, and that we have a diamond spin shoe that's put on the bottom of the casing, and that spin shoe is advanced into the ground, and then those diamonds do cut the ground and allow the casing to advance. Whether we're using driven or spun-in casing, you end up cleaning out the inside with the trico and roller bit. Not sure why that switched there. You advance the casing with, you clean out the casing with the trico and roller bit. When you're spinning the casing with the diamond shoe, and when you're using the trico and roller bit to to clean out the inside of the casing, both methods use water. So it is a little bit tougher in the winter, although not impossible. Our guys just have to be more cautious. And essentially what we do is we just keep the water running all day if we can. That way the water never gets a chance to freeze. Some advantages of the flush joint casing over the holostem augers is they can really advance through cobbles and boulders. The other thing is you have an advantage with the depth. Can be advanced to depths of 300 feet or greater depending on the soil conditions that we're encountering. They also provide a stable hole for any specialty testing. They're really good for when we go to put in wells, because we know for a fact that the well is going to go down straight. So one of the primary methods we use for sampling, whether we're using the holostem augers or the flush joint casing, is to do a split spoon sample. Split spoon sampler is done in accordance with ASTM 1586. And what we're doing when we do a split spoon sample is you're driving the split spoon sampler into the ground using a 140-pound hammer falling 30 inches. That is a standard wait and fall so that we have the standard energy that is provided to that spoon with each blow. These days, it's almost always done with an automatic trip hammer now, which has a 140-pound weight that's lifted with a chain fall system that's run by hydraulics. The reason we do that is to get consistency. In the, I'll call them the old days when I started here 20 some years ago, what we did was mostly a cat head and rope, where we had a cat head that spun and you had a rope on it and the driller pulled it, raised the hammer 30 inches and let it fall. So there was definitely variability and or loss of energy because of the cat head, where the automatic hammers are much more efficient. We do a test on the automatic hammers to determine the energy transfer, and we're generally 85 to 90% energy transfer. With the cat head and rope method, it's closer to about 60 or 65%. The split spoon sampler is generally driven about a depth of 24 inches, depending on the conditions, and we record the blow counts that it takes to drive at each 6-inch increment. After we get the sample back up to the surface, it's classified in the field by a driller. They also take a portion of a representative portion of the sample and put it in a glass jar and return that back to the lab for additional classification, verification, and any lab testing that might need to be done. Undisturbed samples, and they're undisturbed is in quotes. This is the method that's in accordance with ASTM 1587. Advancing these so-called undisturbed samples is the best that you can get by taking a sample out of the ground. There's truly no such thing as an undisturbed sample once it's removed from the earth, but this is the best that we can do. It's advanced by using a thin-walled tube that's advanced at a slow, steady rate into the soils. It's only really useful on cohesive soils because I forgot to mention in the split spoon sampler, there's a basket in the bottom that retains the soil. It's like a set of fingers that lets the soil go in and doesn't let them come back out. The undisturbed sampler does not have that. Therefore, unless it's cohesive and holds together, it doesn't stay into the tube. These are returned to the lab for multiple analysis. There's a lot of different high-level lab testing that we'll talk about in a little bit that can be done. And again, like I said, it produces the most accurate representation of the in situ condition we can get of any soil sample that we pull out of the ground. So there's question number 3.
You can continue, Adam.
Okay. Question number 3 was, in what type of soil condition is a Shelby tube most conducive? The answer for that would be B, soft clay. So the third method of sampling that we have that we can do with conventional soil borings is to core the bedrock. Again, it's done in accordance with ASTM 2113. And in this case, and our general method of sampling is using a double tube core barrel with a diamond cutting shoe. So similar to the diamond cutting shoe that I was talking about for the casing, only it's got a little bit different matrix that holds the diamonds and allows it to cut the bedrock a little bit easier. The double tube refers to the fact that there's an outer barrel that is attached to the cutting shoe, and that spins at a high rate of speed. And then the sample is, as the cutting is progressed, the sample is retained inside of an inner core barrel, and that inner barrel is on a bearing system so that it's barely spinning or not spinning at all, and that protects the core as it goes up into the cutting head so that it doesn't get damaged by that high speed on the outer side. There are other different core barrels that are out there. There are some triple tube barrels that are useful in certain soil conditions or certain bedrock conditions, sorry. But generally in New York State, we don't need to use those. The samples, once they come out of the ground, we measure them, determine the RQD, store them in a wooden box, and bring them back to the laboratory. And there are certain lab tests that we can do on the bedrock as well. Here's a few pictures of some bedrock coring that we were doing in a rock quarry. This is a quarry that they were looking to expand for, where they were crushing the stone for aggregate for road construction purposes and that type of material. Also gives you an idea of what we refer to as a truck mounted drill rig. This is a tandem axle truck. When we say a truck mounted drill rig, we're generally not talking about something the size of the average pickup truck. This is what we're referring to, which for reference weight wise, this is going to be similar to a fully loaded tandem axle dump truck. So somewhere in the 30 to 40 ton range, depending on how much drill steel and water we have loaded on it. One thing that I didn't really talk about much when I talked about the flush joint casing, one thing I mentioned that it was advanced with water. What I didn't mention was how much. And generally, depending on the conditions, you're going to be anywhere from 100 to 300 gallons to advance the casing 5 feet. Now, there are certain methods that we can use to reuse some of that water at the surface if it's coming back up to the surface, but it doesn't always work that way. And generally, when we're coring bedrock, we're using quite a bit more water. Generally, we're going to be using somewhere in the neighborhood of 300 to 500 gallons per 5 foot of advancement. When we were doing a lot of this rock coring that you see here in these pictures, what's not pictured there, because it was out filling up, was the 3,000 gallon tank truck that they were supplying water for us with. So we've talked about conventional soil borings, which are normally what we see here in New York State. Now we're going to talk about something that's a little bit different. It's not quite as common in this area, although it is in various other parts of the country. And that's cone penetration testing. When we refer to cone penetration testing, what it is we talk about how we push a cone, which in that picture is that silver piece next to the computer that has a whole series of electronic sensors. Inside that cone, which is about 2 feet long, in the bottom portion, we measure the resistance on the conical tip. There's a 6-inch friction sleeve above that we measure the friction on that piece of metal. And then if you look at that cone, there's kind of a ring there. And right around where that ring is, there's a seismic geophone. So we're able to measure the seismic shear wave velocity by creating a wave. So how we do that is underneath the back jacks of the drill rig, we put a steel I-beam in contact with the ground and use the drill rig weight to hold it down. And as we push the cone into the ground, we're pushing it at a slow, steady rate of about 2 centimeters per second. And we stop at various intervals. The rods that we use to push that have a wire that goes up through them, and they're 1 meter length rods. So generally, when we're doing seismic shear wave testing, we do it at either 1 or 2 meter intervals. And what we do is we stop when we get to a depth, and before we add the rod, we take a highly calibrated sledgehammer and we hit the ends of that steel I-beam to create a shear wave. And we use that seismic geophone to record when it arrives at the cone. So if we know the depth and we know the time that it took to get there, we can determine the shear wave velocity. The other parameter that's recorded with the cone penetration testing is the pore water pressure. And that sensor is located just behind the tip, and it measures the water pressure that it sees at that whatever depth it's at. Some advantages of the cone penetration testing: it's fast. Depending on how much time it takes to move between locations, we can easily advance 200 to 400 feet per day. So if you reference that to the Holostem augers that I said is generally 60 to 80, you know, we're, if not double the production, we're going to be 4 times the production. Back around Christmas time, we did a site where we knew we were going to hit bedrock about 60 feet or so. And from the time that we started to the time that we were done, and that included setting everything up and packing it all up, we were on site a little less than 3 hours. So that kind of gives you an idea of what can be done. In that particular location, we were trying to determine the seismic site classification. We knew from past experience that it was loose sands. If I did the seismic site classification for that site based on the SPT N values, we came out with the site classification of E. And since it was a hospital facility and specifically an ER addition, they were concerned about the additional costs due to that low seismic site classification. So we did this testing and we were able to bring it up to a C, so that it actually raised it 2-letter grade, 2 letters. Generally, we see at least 1 letter. This one here, we saw 2. So I know the client was very happy on that because it really saved a lot. It's going to save a lot of money in design and construction for that building. The other thing that cone penetration testing is very good for is for providing data for use in driven pile design, whether it's in soft or loose soils. Sometimes if we're in real soft or loose soils, the SPT value isn't as helpful when it comes to those conditions, because it's we don't get enough information. Where this here, recording continuous information and being able to record low tip pressures and friction sleeves, we're able to get better information. It's very useful in cohesive and sand soils. One disadvantage of cone penetration testing is you are not able to push it into very dense gravelly soils and or bedrock. So as soon as we hit either glacial till or bedrock, we generally have to stop. The other disadvantages, and this comes from most of the geotech engineers I know, are the types that like to play in the dirt. And people ask me what I do for a living. I tell them I make mud pies and I get paid for it. And with cone penetration testing, I don't get that sample to play with. So therefore, generally, I always recommend a combination of methods, whether it be CPT and conventional borings, or, you know, in some form or another, some way to get some samples so that we can see what's there and make sure that what we're seeing with the CPT is accurate when it comes to the soil classification. The other disadvantage is it does require a large drill rig for reaction weight. Generally, we have to use that first all-terrain vehicle I told you, and or one of the trucks. Depending on the soil conditions, we can use the Geoprobe, although we may be limited in how much we can push it, because essentially all we're doing is pushing down and using the drill rig as a reaction weight to allow that to happen. Here's a typical CPT log. If you look at the column on the left, that's your tip resistance, like I said, on that conical tip. And in this one here, you're seeing generally the tip resistance is under 200 tons per square foot until you get down into the 45 to 46 foot range where it jumps up significantly, which generally tells us that we're in, looser materials down to that point. If you look at the graph on the far right, the colored one, those are the soil classification, soil behavior types. And what that is the computer takes the correlation of the tip resistance, the friction value, and the pore pressure, and says, okay, if I have these parameters, this is what the soil should be. It's not necessarily what it is, but it's how it's acting. So again, the second column from the left is the friction, local friction, which is that friction sleeve. Then you have a friction ratio, which is a ratio of the tip resistance to the friction sleeve. The next column over is the pore pressure of the water, the water pore pressure, like I was talking about. And if you know where the water table is, you can actually use that to verify where the water table is, which in this case, it gets down, I'm going to say the water table in this one's somewhere in the 37 foot range where it starts to jump up there. And then the other column that I have on this particular graph is the SPT N value. And what that is, again, similar to the soil behavior type, it's a correlation from the soil parameters, the tip resistance, friction, and pore pressure. It gives you an idea of what the SPT N value should be for that if we were to do a conventional boring. Here's some pictures of doing cone penetration testing on the water. This is one of our barges that we have. The picture on the left is where we're just getting ready to put the cone down in through the casing. When we do CPT on the water, we are always going to have a casing that goes from the barge deck into the mud line. And that's partially to protect the rods and give it some strength in case they start to flex. We don't want to break them. That cone, that in the picture on the right that Aaron's holding, that cone is somewhere between $5,000 and $6,000. So generally, we try not to lose those down the hole. The other thing that you can see in that picture on the left, by the gentleman's knee, is the depth wheel. So what that is a rubber wheel that rides along the side of the rods to measure the depth of how deep we are pushing that into the ground. So there's question number 4.
Please continue.
Okay. So question number 4 was, what type of soil parameter does cone penetration testing determine that conventional borings cannot? And the correct answer is B, shear wave velocity. Another method that we have to use to get soil parameters, depending on the type of conditions that we're looking for and what parameters we're looking for, is to use our Geoprobe, and this is a Geoprobe Model 5400. This is a rig that we've had for quite a while that we recently put on a new truck chassis, as you can see in the pictures. This unit does not have the ability to do SPT-N values. This uses a hydraulic percussion hammer similar to the other Geoprobe that I showed you. And what it advances is a macro core sampler. And the macro core sampler is a 4-foot long sampling tube that has a lexane liner. So as we're advancing it, the sample goes up into that lexane liner, and then we're able to use that that lexane liner to bring the sample back. Either we open them up on site and classify them there, or we can bring them back to the laboratory and classify them there. Originally, this type of a unit was developed for environmental sampling, where all they were looking for was contamination in the ground, and they really didn't care about the blow counts because they were just trying to find the contamination plumes and delineate those conditions. But us geotech engineers got a hold of it and kind of came up with some other parameters that we can determine from it. Because it's so fast to advance a boring, we use it a lot on water line projects and those sewer line type linear projects where we want to give the contractor an idea of what the soils are going to be that they're going to encounter and or determining the bedrock profile. The other thing that we can use it for is determining groundwater elevation. If all we're looking for is, water, we can go around relatively quickly and set a bunch of temporary wells with this rig that allow us to get that good groundwater data. We did a project many years ago at a college campus where they were having a lot of water infiltration issues into the basement of a building. And they were pretty convinced it was coming from the ground when it rained. So what we did was we went around the building and put in, I want to say 6 or 7 wells on the different sides of the building. And we monitored them along with the weather conditions for a period of about 6 months. Every time it rained, we tried to get out and determine what the groundwater levels were. What we actually found was the groundwater never came up when it rained, and that the leaking into the building was caused by actually the roof drains had eroded away in the basement. And so it was rainwater, but it wasn't coming from the ground, it was coming from the pipes inside the building. Another method we have to get subsurface soil conditions is test pits. Test pits have a lot of advantages. They're really good on fill sites. If we're trying to investigate whether or not the fill is able to be reused and or how bad it is, sometimes it's hard to see how bad the fill is with the boring. We're generally only taking samples with a 2-inch split spoon, so it may not get a good representation of that fill, and we may see some organic material, but we may not realize that it's maybe all organics, or maybe there is just a little bit of organics, where digging a test pit allows us to be able to see that information better. For certain types of projects, it can actually give us better information on the groundwater. Certainly a test pit, sometimes advanced on a site where groundwater is going to be tough, maybe during a pre-bid meeting, gives the contractor an idea of how fast water is going to flow into the hole, so they can determine how they're going to advance their project and their foundation excavations. The other thing that we do a lot with it is collecting bulk samples that we bring back for lab testing. Disadvantages: you're limited in depth. Generally, we don't dig test pits much more than 10 to 15 feet. And if we need to get into the excavation for any reason, for any of the sampling or testing, we're really limited to about 4 feet because of the OSHA regulations, unless we start getting into trench boxes and such, which gets a lot more expensive. The other thing is we don't determine any of those soil parameters to get the seismic site classification unless we encounter bedrock at a shallow depth. That's another disadvantage. So now we'll talk a little bit about subsurface investigation, or more commonly boring logs. They contain a real wealth of information, all kinds of soil types, consistency, and groundwater information. So if you look at this project here, up at the top, you have information on the project description, where the project was, what the purpose of the boring was. You have a section there with groundwater observations. Those groundwater observations are date and time specific, and that can be important, especially the date, depending on the time of year. If you notice, these water readings were all taken in January, and I can tell you that January in particular, because I remember this project very clearly, was very cold. So those water depths at 6 inches below the surface, that was actually frozen water that we had to break the ice, and then it was solid ice below that. This was in a low area. It's labeled as a parking lot boring, which some people might think we drilled a little bit deep, but that's only because this was originally supposed to be in the building footprint. So if you look at the lower portion of the boring log, on the left-hand side, you have the sampling intervals and then the blows that we had on the split spoon sampler. And then on the right-hand side, you have the soil classifications for those individual samples. This is just page 2 of that same boring. You'll notice that we start to get into better soils on this particular boring around 33 feet. It switches from a clay to a sand, and then we get into a very dense glacial till. This next boring here, the reason I have that shown is if you look down from 8 to 10 feet and then from 14 to 16 feet, you see where we took Shelby tube samples. Again, like I said, these 2 borings were in a parking lot area that was originally supposed to be in the building footprint. And what we did is we did the first boring first, and then that I showed, and then this one next. We were getting the split spoon, the Shelby tube samples so that we could do consolidation testing. And this is where the interaction between the geotechnical engineer and the structural engineer is very important. Because of the conditions we found on the site, we were able to save a significant amount of building costs and not having to put deep foundations in for the building by moving the building on the site. That's why I say these borings were originally supposed to be in the building footprint, and then they moved into the parking lot because they swapped the building in the parking lot, and it was easier to control the settlement in a parking lot than it was underneath the building. This boring log here I put in, it shows you what a rock core looks like. On this particular site, we hit weathered rock from about 1 foot to about 5 feet, and then we cored it from 5 to 10 feet. Generally, your rock cores are going to be 5-foot long runs, unless something goes awry and we have to shorten that. But this gives you an idea of what type of information is recorded on a rock core. So when we start talking about soil classification systems, there's a whole slew of them out there. Your 2 most common, though, are Burmeister and unified soil classification systems. The DOT does have one, although they're getting away from it a little bit. They're using more unified or Burmeister. And then the USDA system is actually becoming more popular because of some of the stormwater manuals referencing that. And that's a USDA system that they have. We'll talk a little bit about the Burmeister and the unified system, not so much the other ones in this presentation. Burmeister is a visual manual procedure. It's performed by geotechnical personnel. Hold on. It's performed by geotechnical personnel in the field. It's also performed in the laboratory by geotechnical technicians or engineering technicians to verify the classifications they get in the field. And again, this is where I say we like to take the sample out and play with it and push it around on the table and see how it rolls. Maybe it rolls out to a real fine ribbon. Maybe it, you know, it's a coarse sample, so it's all gravel, it's all sand. What you have on the screen there is a breakdown in the different particle sizes when we talk about Burmeister soil classification, which starts out with boulders being anything larger than 12 inches, all the way down to microscopic sized clay. There's actually two different ASTMs that reference the Unified Soil Classification System. 2487 is based on a laboratory test. So we actually have to do a sieve analysis where we have different size sieve shakers that we shake the sample down and determine the various weights on each sieve, and that's how we determine the soil classification with that. 2488 is a visual manual procedure that's more similar to a Burmeister, where we're doing it on a visual identification of the particle sizes by weight. This slide here gives you an idea of the part of the Unified Soil Classification, the breakdown, just to give you an idea how the breakdown goes in through, you know, when you have various particle sizes and how to follow the flow chart. So after we go out and do all the investigation in the field, we classify the soils either in the field or in the laboratory. Then we can start doing some of the laboratory testing to get the engineering properties of that soil. The simple and most common test is the natural moisture content, which gives us the percentage of moisture in a sample. The other one that's very simple, I didn't list it on here, is the sieve analysis, which we kind of did, I just talked about. The next one is the Atterberg limits, which are the liquid limit, plastic limit, plasticity index. And these are done on cohesive materials such as clay. And what they do is they determine how the soil is going to react and allow us some parameters to do some quick settlement calcs based on those quick parameters to determine if we need to do higher end lab testing, such as the consolidation potential. If based on the Atterberg limits, it doesn't look like it's going to settle outside the tolerances of that structure, it may not be worth going to the expense of doing the consolidation potential test because the cost is about 10 times what the Atterberg limit test is. The other things that we can determine are the shear strength of the soil and the internal friction angle. And generally, the shear strength, internal friction angle, and consolidation potential are done on Shelby tube samples because they have to be relatively undisturbed, and we're not able to do those on split spoon samples. Once we determine those lab properties, then we can answer every structural engineer's favorite question, is what's the bearing capacity? That's probably the number one question I get asked when I do these geotechnical projects is, hey, can you give me that bearing capacity so that we can get started on our foundation design? The other parameters that we can get are the lateral earth pressures for designing either foundation walls or retaining walls. These parameters can be used to determine slope stability. Using the soil types and the groundwater location, we can determine whether or not frost heave is going to be a potential issue. And then after we have all this information from the field and from the laboratory and whatever calculations that we do on a project, then generally we come up with the geotechnical report. Generally, the geotechnical report has a section in the beginning where we talk about the site and the project description. So if I'm writing the report, generally I'll go to either the architect or the structural engineer to try to get some information on what the building is going to be, the size, the usage, maybe what type of structural system is going to be used, whether it's reinforced concrete masonry, maybe a concrete precast structure, or a steel frame structure. So those may need different parameters depending on different settlement tolerances, depending on how the building is designed. The other thing that's important that goes into the report is discussion of what we did for the field investigation. Basically how many borings we did, how we advanced them, how we sampled them. Then we do a description of the soil and groundwater conditions at the site. And this is a written out description of basically all the information that's on the boring logs. And it gives the reader an idea of what's going on the site. Maybe for those that don't understand a lot of the boring logs or need some quick reference for a project. A little bit on the laboratory testing that we do, and then we go into our section on the engineering findings and recommendations for design and construction of the project. And that's where you're going to find what the bearing capacity is, what the parameters are to use for retaining walls, the different soil properties that we have available, different materials that we recommend for backfill or for slab subbase. And that type of information is in that last section. Other things that geotechnical engineers can do during the project is, one thing I really like to do personally is site visits during construction. It's really nice when you go out after you did a slew of borings on a site and find out that the conditions that are actually there in the foundation excavations are what you expected. And I will say that that's not always the case. There are some times where things come up during excavation, and that's definitely where you should involve the geotechnical engineer for site visits so that you can determine the best way to handle those as quickly as possible so that we don't cause delays with construction. Another thing that has become more popular because of the stormwater stuff is the infiltration testing. Determining how much water the soils can take at particular locations for the stormwater management areas. And then resistivity testing, which is both electrical and thermal. With the green energy initiatives and solar and wind, we tend to do a fair amount of this resistivity testing. And the other area that we see a lot of it is in the infrastructure with the upgrades to some of the power lines. We're doing a lot of electrical resistivity and determining the grounding for the soils. So that takes us to our last question.
And we have one question that's come in that maybe you can answer while they're answering the quiz. The number of borings for water and sewer installation.
That's kind of a tough one. It generally depends on what we think is out there, but we typically do a boring for every 500 to 1,000 lineal feet. But I have done some where we've tried to do, where we've been profiling the bedrock, where we've actually done them about every 100 feet in various areas, especially if bedrock is shallow.
All right, continue. Thank you.
Okay, question number 5. True or false, determining the groundwater table is extremely important. And I guess I didn't hit on this quite as much as I have in other times, but the answer to that is obviously true. There's a lot of things that can be dependent on whether or not we, where the groundwater table is. So here's a couple pictures of our truck mounted drill rigs again. The one on the left is one of our newer rechassied units. Guys kind of wanted to show it off and see how high they could jack it up. The one on the right is an old road bed where we drove out there, but it looks like we floated the rig in the water, so it's just kind of a cool picture.